The first best practice is to use an official and verified Docker image whenever available. Let's say you are developing a Node.js application and want to build it and run it as a Docker image. Instead of taking a base operating system image and installing Node.js, NPM, and whatever other tools you need for your application, use the official Node image for your application. This will not only make your Docker file cleaner, but also let you use an official and verified image which is already built with the best practices. Okay, so we have selected the base image, but now when we build our application's image from this Docker file, it will always use the latest tag of the Node image. Now, why is this a problem? Because this means you might get a different image version as in the previous build, and the new image version may break stuff or cause an unexpected behavior. So latest tag is basically unpredictable. You don't know exactly which image you are getting. So instead of a random latest image tag, you want to fixate the version, and just like you deploy your own application with a specific version, you want to use the official image with a specific version. And the rule here is the more specific, the better. This also gives you and your team a transparency to know exactly what version of the base image you're using in your Docker file. Now, looking at all the image tags or versions here, you see that for Node.js, there are multiple official images, not only with different version numbers, but also with different operating system distributions. So the question is, which one do you choose? And that's an important point. If the image is based on a full-blown operating system distribution like Ubuntu or CentOS, which has a bunch of tools already packaged in, the image size will be larger, right? But you don't need most of these tools in your application images. In contrast, having smaller images means you need less storage space in image repository, as well as on a deployment server. And of course, you can transfer the images faster when pulling or pushing them from the repository. Now, in addition to the size, there is another issue with images based on full-blown operating systems with lots of tools installed inside. And that is a security issue, because such base images usually contain hundreds of known vulnerabilities and basically create a larger attack surface to your application image. And this way, you basically end up introducing unnecessary security issues from the beginning to your image. In comparison, by using smaller images with leaner operating system distributions, which only bundle the necessary system tools and libraries, you're also minimizing the attack surface and making sure that you build more secure images. So the best practice here would be to select an image with a specific version based on a leaner operating system distribution, like Alpine, for example. Alpine has everything you need to start your application in a container, but is much more lightweight. And for most of the images that you look on a Docker Hub, you will see a version tag with Alpine distribution inside. It is one of the most common and popular base images for Docker containers. So the best practice here is that if your application does not require any specific system utilities or libraries, make sure to choose the leaner and smaller images from the selection. The next best practice with Docker is optimizing caching for image layers when building an image. So what are image layers and what does caching an image layer mean? It's very simple actually. Now, Docker image is built based on a Docker file, right? In Docker file, each command or instruction creates an image layer. Let's look at a simple Docker file based on a Node Alpine image. So every Docker image is made up of layers. This means when we use a base image of Node Alpine, like in this example, it already has layers because it was already built using its own Docker file. And you can see that actually in the documentation. When you go to the image page in Docker Hub and click in one of the tags, you will see the layers that make up the image. So this is how the image was built. And plus, in our Docker file, on top of that, we have a couple of other commands that each will add a new layer to this image. And again, this is how every Docker image is created using these multiple layers. And once you build your own application, you can also see all the image layers of the final application image on a command line using Docker image history command with the image name. So this will display you the image layers with the corresponding commands that created this layer. Okay, now what about caching? Well, each layer will get cached by Docker. So when you rebuild your image, if your Docker file hasn't changed, Docker will just use the cached layers to build the image. This, of course, makes building the image much faster. Caching is also useful and important when pulling and pushing an image. So if I pull a new image version of the same application, and let's say 2 new layers have been added in the new version, the whole image doesn't need to be downloaded. Only the newly added layers will be downloaded. The rest are already locally cached by Docker. So they will be reused from the cache. So going back to our simple Docker file example, what we're doing here is that we're copying all the files from the project into the image using the copy command, and then we are executing npm install to install all the project dependencies inside. Now what happens if we make some code changes in our application? Since we are copying everything into the image, this means copy command will be executed again because it needs to copy the changed files, right? All the changes that we made in the code. But the next line of npm install is also re-executed, even though we didn't change anything in the dependencies. Now, why is that? Why isn't it used from cache? Well, that's because once a layer changes, all the following or downstream layers have to be recreated as well. In other words, when you change the contents of one line in Docker file, caches of all the following lines or layers will be busted and invalidated, so each layer from that point will be rebuilt. However, instead we want to take advantage of Docker cache, and we want things that haven't changed to be reused from cache. Again, giving us an advantage that the image will be built fast. So in our case, we don't want to rerun npm install dependencies every time some file in the project changes. We only want to run it when package.json file contents have changed, which includes all the application dependencies. So let's restructure the Docker file to only copy package.json file and then run npm install, and only after that run the copy all the files command. In this case, if we add or remove a dependency in package.json file, it will be copied and npm install will be executed. If we change any other file in the project, these 2 layers will be reused from cache. So npm install will not get re-executed. And you can see that in the output of docker build command as well, where you have the information that a layer has been reused from cache or a layer has been rebuilt. So the rule here and the best practice is that you should order your commands in the Docker file from the least to the most frequently changing commands to take advantage of caching, and this way optimize how fast the image gets built. Now, usually when we build the image, we don't need everything we have in the project to run the application inside. We don't need the auto-generated folders like targets or build folder. We don't need the README file, etc. So how do we exclude such content from ending up in our application image in order to reduce the image size? And that's our next best practice, to use a .docker ignore file. And it's pretty straightforward. We basically just create this Docker ignore file. We list all the files and folders that we want to be ignored. And when building the image, Docker will look at the contents and ignore anything specified inside. But now let's say there are some contents in your project that you need for building the image, so during the build process, but you don't need them in the final image itself to run the application. The way it works is that while you build an image from a Docker file, many artifacts actually get created which are required only during the build time. And this could be development tools and libraries needed for compiling the application, or this could be dependencies needed to run unit tests, could also be some temporary files, and so on. If you keep these artifacts in your final image, even though they're absolutely unnecessary for running the application, it will again result in an increased image size and increased attack surface. A specific example for this is a package.json or pom.xml or any other dependencies file, which specifies all the dependencies for the project and are needed to install those dependencies. However, once the dependencies are installed, we don't need these files in the image itself to run the application. Another more interesting use case is when building Java-based applications, for example, we need JDK to compile the Java source code, but JDK is not needed to run the Java application itself. In addition to that, you might be using tools like Maven or Gradle to build your Java application. Those are also not needed in the final image. So how do we separate the build stage from the runtime stage? In other words, how do we exclude the build dependencies from the image while still having them available while building the image? Well, for that, you can use what's called multi-stage builds. The multi-stage builds feature allows you to use multiple temporary images during the build process, but keep only the latest image as the final artifact. Let's see how that works. This is an example Docker file with two build stages. The first stage, which we call build, specified like this, is used to build the Java application using Maven tool. And in the second stage, which starts from here with directive from Tomcat, we use the files generated in the previous build stage and copy them in the final image. So the final application image is created only in the last stage using these two lines. And all the files and tools that we used in the first stage will be discarded once it's completed. And also we talked about layers. In our case, the final two commands of this Docker file will create the layers of the final image. Again, all of these previous steps will be discarded. So this basically helps us separate the build tools and dependencies from what's needed for a runtime and gives us images which have way less dependencies and are much smaller in size. Now, when we create this image and eventually run it as a container, which operating system user will be used to start the application inside? Well, by default, when a Docker file does not specify a user, it uses a root user. But in reality, there is mostly no reason to run containers with root privileges. And that is also a bad security practice. This basically introduces a security issue because when container starts on the host, it will potentially have root access on the Docker host. So running an application inside the container with a root user will make it easier for an attacker to escalate privileges on the host and basically get hold of the underlying host and its processes, not only the container itself, especially if the application inside the container is vulnerable to exploitation. To avoid this, the best practice is to simply create a dedicated user and a dedicated group in the Docker image to run the application. To create the user and its group, you can simply run user add and group add Linux commands like this. And once you have that user, to also run the application inside the container with that user, you can use a directive called user with the username and then start the application. Conveniently, some images already have a generic user bundled in which you can use, so you don't have to create a new one. For example, Node.js image already bundles a generic user called Node, which you can simply use to run the application inside the container. Finally, how do you make sure and validate the image you built has few or no security vulnerabilities? And so the next and final best practice is, once you build the image, to scan it for security vulnerabilities using the Docker Scout command. Here, note that you have to be logged into Docker Hub to be able to scan your images. So you can do a simple Docker login on your command line and then execute Docker Scout followed by CVEs, and then the image name as a parameter to check for vulnerabilities. And in the background, Docker will run a scan against its own database of known vulnerabilities to run a vulnerability scan on the image. The database of known vulnerabilities gets constantly updated, so new ones get discovered and added all the time for different images. And this is basically an example output of the Docker Scout command, where you see the type of vulnerability, a URL for more information, but also what's very useful and interesting, you see which version of the relevant library actually fixes that vulnerability. So you can update your libraries to get rid of these issues. So these are 8 best practices that you can apply to make your Docker images leaner and more secure. Of course, there are many more best practices related to Docker, but applying these will already give you great results when using Docker in production.